16 is section 12.2, evaluating limits. Yesterday we had an introduction to limits. I'll use by looking at a graph. And so at the very end of the lesson, they started giving me some properties that were concrete ways that we could evaluate limits, algebraic ways that we could do it so that it wasn't just a ballpark guess. The guesses that we were given were educated guesses, but they were still guesses. So when we finished off yesterday, we actually had discovered for ourselves the first two things that they tell us here on page 816. They tell me that polynomial functions are well-behaved and rational functions are well-behaved. Now, remember, for well-behaved, that just means that you can use direct substitution. So, for instance, in this first one, because this is a polynomial, and I know that polynomials are well-behaved, I can just use direct substitution and take -1 and put it in for each of those x values, and the answer that I get will be my limit for that problem. So I don't have to go through and look at a graph or make a table or use properties. Then they also tell me that rational functions are well behaved within their domain. Remember, we were working yesterday with some rational functions, some equations that were fractions, where we would get 0 in the denominator. 0 in the denominator is undefined. So that's not going to be well behaved if I get 0 in the denominator. So that's why they say it's well behaved within its domain. So as long as what I'm plugging in here is not going to give me 0 in the denominator, then I can again just use direct substitution and plug in, and the answer that I get will be my limit. So what happens if they give me something that's not well behaved? Like example 2, we've got a rational function, and we try that direct substitution thing, but that gives me 0 in the denominator. So does that mean my limit does not exist? No, right. It means that it's not well behaved. It might still exist. So today we want to look at, we could always fall back to making a table or looking at a graph, but today we want to get some algebraic techniques for how we could evaluate these limits. My problem is that this rational function is not well behaved. But if I could simplify that function in some way or rewrite it in some way, then maybe it would be well behaved. So one thing that they suggest to me is see if there's any way that you could simplify it down. So if I didn't have this limit notation right here and I just had this rational function and you were told to simplify, what would you do? Factor, right. So I'm going to factor my numerator, and sure enough I end up with a factor in my numerator and denominator that can cancel out. So I'm going to cancel those out, and now I'm left with just x minus 2. That is a polynomial, and so that's well behaved. So I can do direct substitution, and the answer that I get will be my limit. Not an estimate of my limit, not possibly my limit, not a guess of my limit. That is my limit because I algebraically worked it out. That's what they mean by a technique for evaluating limits. If I can find some way to rewrite whatever it is that I have here that is not well behaved, simplify it, factor it, rationalize it, combine it, break it apart, anything that you can think of that you have ever learned in all of your life in mathematics. If there's any way to change that thing around, you might get it to the point that it's well behaved, and then you could just use direct substitution. Now, in AP Calculus, half of our AP exam is multiple choice, but the other half is FRQs, free response questions, where it's not enough just to come up with the right answer. You have to have a justification of your work. You have to have the right notation. For instance, if when you're evaluating a limit, if you don't show the limit from the left and from the right and show that they're equal to each other, you get no credit for that limit. So we want to be very particular about the notation that we use. And with limits, something that we will harp on is the idea that you must recopy this limit notation over and over again until you actually do the direct substitution or you actually evaluate the limit. So when I started, this was my original problem. I didn't plug -3 in for x in this step right here. So I haven't taken my limit yet, so I still need that limit notation. Same idea over here. I'm simplifying my fraction, but I still haven't taken negative 3 and plugged it in for x, so I've not taken my limit yet. I still need my limit notation. However, when I get over here and I do put negative 3 in for x, there should not be limit notation any longer because I've already taken my limit. Okay, so we'll note that as we're going through repeatedly to try and get into that good habit of correct limit notation. All right, look at the next one. For the next one, again, I have a rational function. I know that it's well behaved within its domain, but if I try to plug 0 in, or I'm sorry, if I try to plug 1 in, I get 0 in the denominator. So 1 is not in its domain. It is not well behaved. So let's try what we did a second ago. Let's see if we can simplify this in some way. And since it's a fraction, we might want to try factoring again. So remember that when I have 4 terms, I factor by grouping. Now, to factor by grouping, I'm going to group the first 2 terms and the last 2 terms. I'm going to take a common factor out of the first 2 terms, so that would be an x squared. And I'm going to take a common factor out of the last 2 terms, but really the only thing they have in common is just a 1. To factor by grouping, once I take out those common factors, what I have remaining has to be identical, or I can't factor by grouping. So I can take out that common factor of x minus 1, and then my other factor, remember we've said it's almost like you can put your finger over top of this one, and whatever you have left is your other factor. So the x squared plus 1 would be my other factor. So now that I've got that denominator factored, I can plug it in. And then I can simplify because my x minus 1s will cancel out. So now I want to check and see, is there any chance that that simplified fraction will be well behaved? So if I do direct substitution, because this is a rational function, I'm allowed to do that if it's in the domain. Sure enough, when I plug it in, it works this time. I don't get 0 in the denominator. And so my limit would be 1/2. Now for each one of these, I could always go back and make a table, and I could always go back and look at a graph, and it would enforce what we're getting for our answers here. All right, look at the next one. Example 4, I've got a fraction, but this time I've got a radical in it. Can I cancel those x's? No, because one of the x's underneath the radical, I can't cancel it with the one that is sitting alone in the denominator. I could try direct substitution, but I can easily see that its domain is all real numbers except for where I'm going to get a 0 in the denominator or a negative under a square root. So 0 in the denominator is obviously when x is equal to 0. So if I try and do direct substitution, not going to work. All right, well, let me try that factor and cancel thing. I'm not sure how you're going to factor that. So we need something different from our algebraic bag of tricks. What they suggest to me here is, you know how when we have a radical in the denominator, we rationalize the denominator, we multiply by the conjugate? Why couldn't you do that to the numerator since you've got a radical in the numerator? Why in the world would I want to do that? Because my goal is to change this thing in any way that I possibly can. So the same way that we would rationalize a denominator by multiplying by the conjugate, I'm going to rationalize my numerator by multiplying by the conjugate. Now remember that a conjugate has the exact same numbers but just the opposite sign, like square root of x plus 1, square root of x plus 1. 1, 1. The only difference is if this sign is minus, then this sign will be plus. And of course what I do to the numerator, I do to the denominator. All right. So if we multiply our numerators, I'm going to have to FOIL. So square root of x plus 1 times square root of x plus 1 is just going to give me x plus 1. Square root of x plus 1 times a positive 1 and square root of x plus 1 times a negative 1 are going to drop each other out. And negative 1 times positive 1 is going to be negative 1. Anytime I multiply by a conjugate, it's just a difference of squares, right? So it's going to end up being the first term squared minus the second term squared. So that might save me a little bit of time and energy. All right, so where do I go from here? I did that rationalizing thing. Does that help me? What do I do now? Okay, simplify that top. So 1 minus 1 would be 0. So that would just leave me x in the numerator. Then what? I can cancel the x in the numerator and the denominator. Now that's a happy thing because remember it was that x in the denominator that was causing me trouble. So now I'm going to go back and check and see, hey, is there any chance that that made it well behaved? Well, let's plug in and see. And when I do, remember that they had told us one of our properties yesterday is that if you have a radical that you can use direct substitution as long as you get for a square root a number greater than 0. We did when we did our square root here, we got the square root of 1, so that's okay. That's going to be well behaved. I can use direct substitution. And so my exact limit is 1/2, not an estimate, not an approximation. So anything that I can think of from algebra, simplifying, factoring, rationalizing, anything that might help. Even with all of those things in our algebraic bag of tricks, there are still some times that I hit a problem that I cannot figure out algebraically. Like if you look at example number 5. For example number 5, we've got the limit as x approaches 0 of the quantity 1 plus x to the 1 over x. First, I don't even have a fraction, so I can't factor my numerator and denominator and get stuff to cancel out. I don't have a radical, so I can't rationalize by multiplying by the conjugate. I can't see any way to simplify this. So that's why it's nice to have section 12.1 to fall back to, because I can always go back to making a table of values, or I can always go back to looking at a graph. So for this one, we make a table of values. Since we're approaching 0, those are those same numbers that we've worked with all along. And so we can fill in our table. There are some times that even when I complete my table, I may have a little bit of a question about my limit. Like in a lot of the ones that we were working with yesterday, we recognized a pattern. It was very clear what was happening. But when I get here, I've got 2.7196, and when I get here, I've got 2.7169. Yes, I could round both of those to 2 decimal places and they would be equal. It would be 2.72. But in AP Calculus, we have to have 3 decimal place accuracy. So what I could do is continue going with my table, like I could put in a negative 0.0001 and a positive 0.0001 and see if that gives me 3 decimal place accuracy. Or something else that they suggest to me is if you know that your limit is in between these 2 values, you could find the mean of those 2 values. So they added the 2 innermost values, the closest approximations that we had to this point. They added those and divided by 2, and that gave us an approximate value of 2.71825. That actual limit, if we kept going and going and going with our table, that actual limit is 2.71828. And if that's looking familiar, that is the approximate value for E, and that's coming from where we get our definition from E as well. All right, look at example 7. Yesterday, we talked about one-sided limits, limits from the left and limits from the right, that the limit from the left has to equal the limit from the right or the limit doesn't exist. We looked at piecewise defined functions, we looked at absolute value functions, and we said that anytime you have an absolute value, it is going to be a piecewise defined function. So when I'm looking at example 7, I've got the limit as x approaches 0 of the absolute value of 2x over x. Because that's got an absolute value, the first thing I need to do is go redefine that function into its pieces. So I can think about, okay, if what's inside the absolute value, 2x, is positive, so where x is greater than 0, I'm going to get exactly what I started with. So I would get 2x in my numerator and my denominator stays the same. But if what's inside the absolute value 2x is less than 0, so where x is less than 0, I'm going to get the exact opposite of what I started with. I'm going to get opposite of 2x, or negative 2x, in my numerator, and my denominator would stay the same. Now, we could simplify each of those down a little bit, like 2x divided by x is just 2, and negative 2x divided by x is just negative 2. So there is our piecewise defined function. So now we want to find the limit as we're approaching 0. And I have to check that limit from the right and from the left and make sure they're the same. So let's start from the right. if I'm approaching this from the right-hand side, am I going to use the top piece of the function or the bottom piece of the function? If I'm approaching from the right. The top, Because if I'm approaching from the right, that means that I'm approaching 0 from like 2, 1, 0.5, 0.1, 0.01. All of those are values greater than 0, so that means that I would use this top equation. All right, I'm going to try direct substitution because that's a rational function. So I tried direct substitution, doesn't work. I get 0 in the denominator. But using the same method that we've been doing all day today, if direct substitution won't work, then we simplified, right? So 2x divided by x gives me 2. Yesterday, that didn't help me. But today it does, because yesterday at the very end of the lesson, we picked up a property about the limit of constants. What's the limit of a constant? That constant, right. So I can say, okay, the limit of 2 is 2, and I wouldn't have to build a table this time. All right, what if I'm approaching 0 from the left-hand side? Am I going to use the top piece or the bottom piece? The bottom piece, right, because from the left-hand side, that's going to be like -1, -0.5, -0.1, -0.01. All of those are values less than 0, so I would be using that -2x over x. Rational function, but it's not well behaved because 0 is not in its domain. So I can't use direct substitution. So instead, I do what I've been doing today. I simplify that fraction. -2x over x is -2. And now I can take the limit of -2 and get -2. So the limit from the right was +2. The limit from the left is -2. So what is this limit? Limit from the right is +2. Limit from the left is -2. So what's the overall limit? It does not exist, right? Because remember we said when the limit from the left doesn't equal the limit from the right, then the limit doesn't exist. Now, we can put what we've learned today in conjunction with what we learned yesterday, because if we were to go back and put absolute value of 2x over x into our calculator, this is the graph that it would generate. If I look at that graph, very similar to the one that we saw yesterday, where we can say, okay, as I'm approaching 0 from the left and from the right, this is not all converging on one particular value, right? I don't have both pieces of my graph coming together at one point. They're going off in two different directions, so that's not a target or a bullseye. I also could build a table of values where every single negative number that I put in, I would plug into the equation where x is less than 0, so I'd get -2 every time. So that limit from the left would be -2. When I did the limit from the right, all of those values that I plugged in would be positive, so I'd be plugging them into this top equation and getting +2 every time. So again, because the limit from the left didn't equal the limit from the right, I would know that the limit did not exist. So what we learned yesterday goes hand in hand with what we're doing today, and they reinforce each other. All right, look at another piecewise defined. Example number 8, they tell me find the limit as x approaches 1 for this piecewise defined function, defined where x is less than 1 and x is greater than 1. So if I'm going to take the limit as x approaches 1 from the right-hand side or from the positive side, am I going to use the red piece or the green piece? The green, right, because that's where the values are greater than 1. If I'm approaching 1 from the right-hand side, I'm using like 2, 1.5, 1.1. Those are all values greater than 1. So when x is greater than 1, I'm supposed to use 4x minus x squared. So how do I evaluate a limit for something that looks like that? Four x minus x squared. What is 4x minus x squared? It is a polynomial, right? What do we know about all polynomials? They're well behaved, so I can do direct substitution. Yes, so I could factor, absolutely, but I don't need to because I can just do direct substitution and go straight to my answer. All right, how about if I'm approaching 1 from the left-hand side? Am I going to use the red piece or the green piece? The red piece, right, so I'm going to use the equation 4 minus x. How do I evaluate that limit? Direct substitution, right, because it's a polynomial. I can use direct substitution, and I'll get my limit. So the limit from the right was positive 3, and the limit from the left was positive 3. So what's this limit? 3, yes. So I don't want us thinking that every piecewise defined function is always going to be does not exist. Here's a piecewise defined where the limit did exist, because look at your graph. As you're approaching 1 from the right-hand side and from the left-hand side, both pieces of that graph are converging on the same y value. They're converging on 3. So that's why we got a limit. Whereas up here, as we approach 0, this was approaching positive 2 and this was approaching negative 2. They weren't both converging on the same y value. And we could also build a table if we wanted to for this one, and we would get 3 from the left and from the right. All right, look at example 9. Example 9 gives us a real-world application of these one-sided limits. So example 9 says an overnight delivery service charges $8 for the first pound and $2 for each additional pound. Let x represent the weight of a parcel and let f of x represent the shipping cost. So to begin with, we're going to need to build a function for this thing, and then they want me to evaluate the limit as x approaches 2. Okay? So they told me that if my parcel weighed between 0 and 1 pound, so all the way up to 1 pound, how much did it cost? $8, right. If I'm over 1 pound going up to 2 pounds, how much is it going to cost? $10, right, because it's $2 for the additional pound, right? And then if it's over 2 pounds going up to 3 pounds, how much would it cost? 12, because we're going to have to add another $2, right? So if I wanted to graph that, then over here, from 0 to 1, I would be at 8. From 1 to 2, I would be at 10. And from 2 to 3, I would be at 12. And so we've color-coded those to match our equations over here with their graphs over here. All right, so they want me to evaluate the limit as x approaches 2. All right, so if I'm approaching 2 from the right-hand side, that means my package weighs 2.3 pounds or 2.1 pounds. How much is that going to cost? 12, right, because we said if it's between 2 and 3, if it's greater than 2 and less than 3, that it's going to be $12. If I approach 2 from the left-hand side, that means my package weighs maybe 1.5 pounds or 1.7 pounds or 1.9 pounds. How much is that going to cost me? $10, right, because if it's between 1 and 2, then it costs $10. So if the limit from the left is 12, then what's the limit? Does not exist. There is not one. And if I look at the graph right here at 2, my green graph and my red graph are not converging on the same value. If I build a table of values where I went through and I looked at different packages of different weights as I approached 2 from the left, all of them are going to cost me $10. If I looked at packages as I approached 2 from the right, all of them are going to be a little more than 2 and they're going to cost me $12. 10 doesn't equal 2. So my limit does not exist. All right, last thing we want to look at today, example 10, is something that we have done repeatedly this year, all the way back to chapter 1. It was called a difference quotient. And every time we saw it, it had that little icon that you see there on page 823 that said that it was an application to calculus. That's what that icon meant. And so they would ask me to do something like f of x plus h minus f of x divided by h. Or they'd put a number in like we've done here, f of 3 plus h minus f of 3 divided by h. So let's review that, even though we've seen that several times this year. Let's just get it back fresh in our memory. So when they say find f of 3 plus h, and they give me this equation for f of x, that means that they want me to put 3 plus h in the place of x, right? So let's go through and let's put 3 plus h in the place of x. So that would be 3 plus h squared minus 1. So 3 plus h squared, I'm going to have to FOIL that out, right? So 3 times 3 is going to give me 9. 3 times h is going to give me 3h. And h times 3 is going to give me another 3h, so 6h. And then h times h is going to give me h squared. And then we had our minus 1. So simplify that a little bit. 9 minus 1 is going to give me 8. Put it in descending power order, and there's f of 3 plus h. Then they also asked me to find f of 3. If I'm trying to find f of 3, that just means put 3 in the place of x. So I'll come up here and put 3 in for x. So that's going to give me 3 squared minus 1. So 9 minus 1 is going to give me 8. So now I have all the components that I need to do my difference quotient. Because for my difference quotient, they said do f of 3 plus h. All right, here's what we got for f of 3 plus h. H squared plus 6h plus 8. Then it says subtract from that f of 3. All right, for f of 3, we got 8. So we'll subtract 8. And then divide that whole thing by h. Okay, we'll divide it by h. So we're just following the pattern that they gave us there. So 8 minus 8 would give us 0. And then if I continue simplifying, since every one of these pieces has an h in it, I could factor that h out of the numerator and cancel it top and bottom to get h plus 6. So that's our difference quotient that we've seen repeatedly. Why did they tell us every time that we saw this that this was going to be an application for calculus? Because in calculus, what we want to do is we want to take the limit of that difference quotient. So I'm going to add that component of a limit out in front of that exact same problem that we just did. Just a second ago, we did f of 3 plus h minus f of 3 divided by h, and we got the answer to that was h plus 6 or 6 plus h. So now I have the limit of 6 plus h. That's a polynomial. I can do direct substitution. So I'm going to put 0 in the place of h, and I'm going to get 6. What we just got right there is a derivative. And remember we talked about yesterday that differential calculus is the calculus of derivatives, and that's what we spend the majority of Calculus 1 doing. So that is a derivative, and that's why that difference quotient was so important this year that they had us keep doing it. All right, so here is our homework for tonight on pages 824 to 825.